Picture this: you're standing on the dusty, rust-colored surface of Mars, the first human to ever set foot on this alien world. The horizon stretches endlessly, a stark and breathtaking landscape unlike anything on Earth. But then, without warning, your spacesuit, the only thing separating you from the deadly environment, starts to fail. The air thins, the cold seeps in, and the fragile barrier between life and death begins to crack. This isn't a scene from a blockbuster movie. It's a very real problem that engineers and scientists are racing to solve right now. Because if we're ever going to call another planet home, we'll need spacesuits that can handle the unimaginable. The suits that took astronauts to the moon half a century ago were marvels of their time, but they were designed for brief excursions in a relatively forgiving environment. Today, as we set our sights on Mars and beyond, we're facing conditions far more extreme: toxic atmospheres, crushing pressures, temperatures that swing from blistering heat to deep freeze in minutes. Surviving out there will require a complete reinvention of the spacesuit, blending advanced materials, artificial intelligence, and even bioengineering to create something that feels less like a bulky suit and more like a second skin. So how do we build something that can withstand alien worlds? The answer lies in a hidden world of science, where researchers are pushing the boundaries of what's possible. From self-healing fabrics that repair themselves to smart systems that predict failures before they happen, the next generation of spacesuits will be nothing short of revolutionary. And in this video, we're going to uncover exactly how these innovations work and why they might be the key to unlocking humanity's future among the stars. This isn't just about better gear, it's about reimagining survival itself. So let's dive in. The first spacesuits weren't built for walking on distant planets. They were essentially high-tech pressure balloons, designed to keep astronauts alive in the vacuum of space for just a few hours at a time. Take the Mercury suits from the early 1960s, for example. They were modified versions of military jet pilot gear, stiff, heavy, and barely flexible enough for basic tasks. Astronauts could hardly move their arms or legs, let alone scramble across rocky terrain or set up a research station. But back then, survival was the only goal. Fast forward to the Apollo missions, and suddenly, suits had to do more. The moon's surface was a brutal mix of razor-sharp dust, extreme temperatures, and punishing radiation. Engineers responded with the iconic white A7LB suit, a marvel for its time, with layers of insulation, a liquid cooling system, and boots tough enough to handle lunar soil. Yet even these suits had limits. Walking was clumsy, bending took enormous effort, and after just a few hours outside, astronauts were exhausted. Now compare that to what we'll need on Mars. A single mission could last 2 years, with astronauts facing sandstorms that last months, temperatures dropping to -80 degrees Celsius, and radiation levels far beyond Earth's protective magnetosphere. Traditional suits would be a death trap. They're too rigid for daily labor, too fragile for abrasive Martian dust, and nowhere near smart enough to handle emergencies on their own. That's why the next leap in spacesuit technology isn't just an upgrade, it's a revolution. Instead of bulky, one-size-fits-all designs, researchers are working on modular suits that can adapt to different tasks, self-repairing materials that patch tiny punctures before they become disasters, and even biometric systems that monitor an astronaut's health in real time. The goal, a suit that doesn't just protect but enhances human capability, turning explorers into true pioneers of alien worlds. And that's not science fiction, it's the next chapter in our journey to the stars. To understand why today's spacesuits would fail on Mars or Europa, imagine trying to hike through a desert wearing a suit of armor, one that wasn't designed for walking. That's essentially the problem astronauts will face with current designs. Built for the weightless void of space, these suits prioritize pressurization over practicality when it comes to alien terrain. Take mobility, for example. Modern suits rely on rigid layers to maintain internal pressure, forcing astronauts to fight against their own gear just to bend an elbow or kneel down. On the Moon, this was a nuisance. On Mars, where crews might need to climb rocky slopes or repair equipment for hours, it could be crippling. Then there's the dust, not the soft, powdery stuff you'd brush off a shelf, but jagged, electrostatic particles that cling to everything. Martian soil contains perchlorates, toxic chemicals that can damage lungs if tracked into habitats. Existing suits weren't built to repel this kind of abrasive grit, and their fabric layers could degrade over time, like sandpaper grinding away at a jacket. Worse, that dust could jam zippers, clog joints, or even short-circuit electronics. The Apollo crews learned this the hard way when lunar dust wore through their glove layers in just a few days. On a 2-year Mars mission, that kind of wear could turn deadly. And let's talk about temperature. In space, suits deal with extreme heat or cold, but rarely both at once. On Mars, daytime temperatures might reach a balmy 20 degrees Celsius near the equator, only to plunge to -70 at night. Europa's icy crust is even harsher, with surface temps hovering around -160 degrees Celsius. Current thermal systems designed for steady conditions would struggle to adapt, overheat during the day, and astronauts risk exhaustion, freeze at night, and critical components could fail. But perhaps the biggest oversight, these suits aren't smart. They can't detect a slow leak in real time or adjust insulation when a sandstorm rolls in. They're passive shields, not active partners in survival. That's the real lesson here. Surviving alien worlds isn't just about making suits tougher. It's about making them smarter, more adaptable, almost alive. Because out there, a split-second decision could mean the difference between coming home and becoming part of the planet's landscape. The secret to surviving alien worlds might just lie in fabrics so advanced they seem ripped from the pages of science fiction. Forget the bulky, inflexible materials of old-school spacesuits. Today's breakthroughs in material science are rewriting the rules of protection. At the forefront are self-healing polymers, materials that can automatically repair small punctures or tears, much like human skin stitches itself back together after a cut. Picture a suit that detects a tiny breach from a micrometeorite and instantly activates microscopic healing agents to seal the gap before an astronaut even notices. This isn't magic, it's chemistry engineered at the molecular level, where specially designed polymers realign their bonds when damaged, closing the wound in minutes. On Mars, where a single tear could spell disaster, this technology could be the ultimate lifeline. Then there's graphene, the so-called wonder material. Lighter than a feather yet stronger than steel, graphene-infused fabrics could revolutionize how we shield astronauts from cosmic radiation, one of the deadliest threats in space. Traditional shielding relies on heavy metals like lead, which add crippling weight to suits, but graphene's unique atomic structure can block radiation while remaining paper-thin, allowing for suits that are both safer and far more agile. Some prototypes even incorporate layers that actively neutralize radiation by converting harmful particles into harmless energy, turning the suit itself into a dynamic shield. But perhaps the most ingenious innovations come from biomimicry materials that borrow tricks from nature. Imagine fabrics inspired by the scales of deep-sea fish, which withstand crushing pressures, or by desert beetles that harvest water from thin air. Researchers are already testing textiles that mimic these adaptations, creating suits that can regulate moisture, resist extreme pressures, and even extract trace water from alien atmospheres. One experimental design uses microscopic channels to wick away sweat and recycle it into drinkable water, a game changer for long-duration missions. And let's not forget smart textiles woven with nanotechnology. These fabrics can sense changes in their environment, like a sudden drop in temperature or a spike in radiation, and adjust their properties in real time. A suit might stiffen its joints to support an astronaut climbing a rocky slope, then loosen up for delicate equipment repairs. Some prototypes even integrate flexible electronics that monitor vital signs, alerting the wearer to dehydration or fatigue before they become critical. The challenge now isn't just inventing these materials, it's making them work together seamlessly. A Mars-worthy suit might layer self-healing polymers for durability, graphene for radiation shielding, and biomimetic fabrics for environmental adaptation, all controlled by embedded smart systems. It's a staggering engineering puzzle, but the payoff is monumental. A suit that doesn't just keep astronauts alive, but empowers them to thrive in the harshest corners of the cosmos. These aren't incremental upgrades, they're the foundation of a new era in exploration, where the right fabric could mean the difference between planting a flag and becoming part of the landscape. Imagine a spacesuit that doesn't just sit there. It thinks, reacts, and even anticipates danger before you do. That's the promise of AI-driven smart suits, where wearable tech transforms bulky gear into an intelligent partner. At the heart of this revolution are embedded sensors, tiny but powerful enough to track everything from oxygen levels to muscle fatigue. These aren't just passive monitors. They're wired into machine learning algorithms that analyze data in real time, spotting patterns humans might miss. If your heart rate spikes during a climb, the suit could automatically adjust its cooling system, or even suggest a rest break before exhaustion sets in. But the real game changer, predictive maintenance. Traditional suits fail without warning, leaving astronauts vulnerable. Smart suits, though, use networks of microsensors to detect wear and tear on critical components, say, a weakened seam or a failing oxygen regulator. The AI compares this data against thousands of simulated failure scenarios, flagging issues long before they become emergencies. Picture a glove joint showing early signs of abrasion. Instead of waiting for a blowout during a spacewalk, the suit alerts the crew to repair it during routine maintenance. It's like having a mechanic built into the fabric. Then there's haptic feedback, subtle vibrations or pressure cues that guide astronauts without overwhelming them. On Mars, where dust storms can obscure vision, a suit might pulse on the left side to signal an approaching hazard. Or during complex repairs, gentle taps could indicate the correct torque for tightening a bolt, turning the suit into a real-time instructor. Some prototypes even experiment with augmented reality displays projected onto the visor, overlaying terrain maps or equipment schematics so astronauts can work hands-free. The most radical idea, suits that learn from their wearers. Machine learning algorithms could adapt to an astronaut's movement patterns, easing joint resistance for someone favoring an old injury or stiffening support during heavy lifting. Over time, the suit becomes a custom-fit extension of the body, fine-tuned to individual needs. This isn't just about adding gadgets, it's about redefining safety. A smart suit could cross-reference biometric data with environmental sensors, recognizing that a sudden drop in external temperature means a sandstorm is near. It might then seal vents proactively or switch to battery-conserving mode. In a crisis like a sudden pressure leak, AI could override manual controls to prioritize survival, sealing layers and rerouting oxygen in milliseconds. The challenge now is making these systems reliable enough for life or death situations. A glitchy sensor or a delayed alert could be catastrophic. That's why NASA and private firms are testing redundancies backup networks that kick in if primary systems fail. The goal, a suit as trustworthy as a fellow astronaut, one that doesn't just react but truly collaborates, because when you're millions of miles from home, your best chance of survival might just be the suit on your back, thinking right alongside you. Breathing on Mars sounds simple until you realize the air is 95% carbon dioxide, with barely a trace of oxygen. Earth's atmosphere is a life-giving cocktail we take for granted, but on alien worlds, every breath must be engineered. That's where closed-loop life support systems come in, meticulously designed to recycle every molecule of oxygen, scrub out toxins, and mimic the delicate balance of Earth's biosphere. The stakes couldn't be higher. One malfunction and astronauts are left gasping in a vacuum or poisoned by their own exhaled breath. Traditional systems, like those on the International Space Station, rely heavily on resupply missions. Water is split into hydrogen and oxygen through electrolysis, while carbon dioxide is scrubbed chemically, a process that's efficient but fragile. On Mars, where resupply could take years, we need systems that can sustain themselves indefinitely. Enter algae bioreactors, where tiny photosynthetic organisms become the unsung heroes of survival. These microfactories absorb carbon dioxide and sunlight, churning out fresh oxygen while even producing edible biomass. It's like turning every astronaut into a gardener, tending to their own oxygen supply. Early prototypes have already proven astonishingly effective. Some strains of cyanobacteria can thrive in Mars-like conditions, offering a self-renewing lifeline. But algae alone won't cut it. That's why engineers are layering in electrochemical scrubbers, devices that strip carbon dioxide from the air and convert it back into breathable oxygen using just electricity. Unlike bulky chemical filters, these scrubbers are lightweight, scalable, and precise enough to adjust output based on crew demand. Pair them with advanced moisture recyclers that extract water from sweat, urine, and even exhaled vapor, and suddenly, the system starts to resemble a miniature Earth, a self-sustaining bubble of habitability in an otherwise lethal environment. The real breakthrough, though, is redundancy. The best designs interweave multiple systems, so if one fails, another picks up the slack. Imagine a Martian habitat where algae tanks provide baseline oxygen, scrubbers handle peak demand during physical labor, and backup chemical cartridges stand ready for emergencies. It's not just about efficiency, it's about resilience. Because when you're 34 million miles from the nearest hardware store, every breath depends on technology that refuses to fail. And then there's the wild card, terraforming on a personal scale. Researchers are experimenting with suits that integrate photosynthetic coatings, turning sunlight into oxygen right on the fabric. Others explore symbiotic systems where wearers' movements generate power to run air recyclers, blurring the line between human and machine. The goal: a future where breathing on Mars feels as effortless as it does on Earth, where every inhale is a silent triumph of engineering over the void. This isn't just about survival. It's about turning alien atmospheres into something habitable, one molecule at a time, because the real challenge of living on another world isn't just getting there, it's staying alive once you arrive. A spacesuit is a paradox. It must be tough enough to shield its wearer from lethal environments, yet flexible enough to allow them to climb, kneel, and work for hours without exhaustion. Striking that balance is one of the hardest challenges in suit design. Too rigid, and astronauts waste precious energy fighting their own gear. Too pliable, and a single sharp rock could puncture the barrier between life and vacuum. The solution might lie in hybrid designs that blend the best of both worlds, rethinking protection from the ground up. Take mechanical counterpressure suits, a radical departure from traditional bulky designs. Instead of relying on gas pressure to inflate the suit like a balloon, these prototypes use tight, elastic layers to apply direct pressure to the skin, almost like a second set of muscles. The result, unprecedented freedom of movement. Astronauts could bend, crouch, and even jog with near-Earth agility, all while maintaining the pressure needed to survive. Early tests are promising, but there's a catch. The suit has to fit perfectly. Any gaps or wrinkles could create dangerous pressure imbalances, so researchers are exploring smart materials that dynamically adjust their tension, molding to the body like a living glove. Then there's modular armor, inspired by medieval knights and deep-sea crustaceans. Instead of a single, inflexible shell, these suits use overlapping plates that slide and pivot as the wearer moves. Need to collect samples on hands and knees. The knee joints lock into a reinforced mode. Climbing a steep ridge, the shoulder segments stiffen for support. This isn't just about durability, it's about adaptability. Some prototypes even incorporate shape memory alloys, materials that change stiffness in response to heat or electric currents, allowing the suit to shift from flexible to rigid in seconds. But the ultimate test is real-world conditions. On Mars, where dust seeps into every crevice, joints must stay sealed while flexing thousands of times. In Europa's sub-zero ice fields, materials can't become brittle or crack under strain. That's why labs are putting prototypes through brutal simulations, abrading them with volcanic sand, freezing them in vacuum chambers, and bombarding them with radiation. The goal, a suit that moves like a gymnast's leotard but protects like a fortress. The payoff goes beyond comfort. Agile suits could revolutionize planetary science, letting astronauts traverse mile-wide craters, scale cliff faces for pristine rock samples, or navigate icy caverns in search of microbial life. Every step wouldn't be a struggle, it'd be an opportunity. And that's the real breakthrough, when survival gear stops being a limitation and starts becoming an extension of human ambition. After all, the future of exploration isn't just about reaching new worlds, it's about thriving on them. Surviving the temperature roller coaster of alien worlds isn't just about staying warm or cool, it's about mastering a relentless back and forth between extremes that would shatter ordinary materials. On Mars, a single day can swing from a mild 20 degrees Celsius to a bone-chilling -73 by nightfall. Europa's icy crust, even more brutal, with temperatures hovering around -160. And that's not even counting the searing heat of direct sunlight in a vacuum, where surfaces can rocket to over 100 degrees in minutes. Traditional insulation simply can't keep up. The next generation of spacesuits will need something smarter, something that adapts in real time like living tissue. Enter phase change materials, substances that absorb or release heat as they shift between solid and liquid states. Picture a suit lined with microscopic wax capsules embedded in its fabric. When temperatures soar, the wax melts, absorbing excess heat like a sponge. When night falls and the cold sets in, the wax solidifies again, releasing stored warmth back to the wearer. It's nature's own thermostat. Think of how our bodies sweat to cool down or shiver to generate heat, but engineered into every layer of the suit. Researchers are already testing prototypes with materials like paraffin and salt hydrates, fine-tuning them to handle the specific extremes of Mars or the Moon. But phase change alone isn't enough. That's where microfluidic cooling comes in, a system of tiny, branching channels woven through the suit, circulating coolant like a network of miniature rivers. Unlike the bulky, rigid tubes in older suits, these channels are flexible and precise, able to direct cooling exactly where it's needed. An astronaut working under the harsh Martian sun might have coolant flow intensify along their back and shoulders, while their legs receive less, conserving energy. And because the system is dynamic, it can adjust on the fly, rerouting flow if a sandstorm suddenly plunges temperatures. Some designs even integrate biometric feedback, linking the cooling rate to the wearer's heart rate or skin temperature for near-instant comfort. The real breakthrough, though, is combining these technologies with active heating elements. Thin, flexible heating grids lighter than a sheet of paper can be sandwiched between suit layers, powered by compact batteries or even solar patches on the suit's exterior. On Europa, where shadows mean instant deep freeze, these grids could keep critical joints from stiffening, ensuring astronauts retain full mobility. And for emergencies, some prototypes incorporate exothermic chemical packs, like those in hand warmers but scaled up, ready to ignite a burst of heat if primary systems fail. Testing these systems isn't for the faint of heart. Labs simulate Martian conditions with vacuum chambers that alternate between blistering heat and cryogenic cold, while robotic arms flex suit joints thousands of times to mimic years of wear. The goal, a suit that doesn't just endure these extremes but makes them feel routine. Because comfort isn't a luxury in space, it's the difference between a focused, productive astronaut and one battling exhaustion or hypothermia. The future of thermal regulation isn't just about survival. It's about giving explorers the freedom to work seamlessly in environments that would kill an unprotected human in minutes. Imagine a scientist on Mars kneeling to collect samples at high noon, then hours later, standing unfazed under a starry, sub-zero sky, all because their suit quietly, relentlessly recalibrates itself to the world around them. That's the promise of these technologies, not just surviving alien climates but conquering them. Martian dust doesn't just cling, it invades. Unlike the coarse, gravelly particles on the Moon, this dust is finer than talcum powder, with grains so small they behave more like a toxic gas than soil. Every step kicks up clouds that hang suspended in the thin atmosphere, seeping into seams, clogging vents, and coating surfaces with a corrosive blanket. But the real danger isn't just the grit, it's the chemistry. Mars dust is laced with perchlorates, salts so harsh they can burn human skin and damage lung tissue if inhaled. For astronauts, this isn't a nuisance, it's a slow-moving disaster. A single mission could expose them to years of accumulated exposure, turning their habitat and even their suits into a ticking time bomb of contamination. Traditional dust solutions, like the brush and vacuum methods used on the Moon, won't cut it here. Martian dust is electrostatically charged, sticking to surfaces with a stubborn grip. That's where innovation kicks in. The latest suit prototypes integrate electrostatic repulsion systems, lining critical joints and seals with materials that generate opposing charges. Picture a force field at the microscopic level, pushing dust particles away before they can latch on. Some designs take inspiration from nature, mimicking the way lotus leaves repel water with microscopic ridges that prevent adhesion. These hydrophobic coatings don't just resist dust, they make surfaces so slick that particles slide off with a gentle shake, like raindrops on a waxed car. But keeping dust outside the suit is only half the battle. Once explorers return to their habitat, they'll need to decontaminate without carrying poison indoors. Forward-thinking designs include airlock dust showers, where suits are blasted with controlled bursts of ionized air to neutralize charges and dislodge particles. Others experiment with self-cleaning fabrics woven with photocatalytic coatings materials that break down perchlorates into harmless compounds when exposed to light, essentially using sunlight to detoxify the suit itself. The stakes couldn't be higher. A single grain of dust wedged in a helmet seal could compromise its integrity over time. Accumulated perchlorates on glove fingertips might transfer to food or equipment, turning routine tasks into health hazards. And if dust infiltrates life support systems, it could trigger cascading failures from clogged filters to short-circuited electronics. This isn't just about engineering, it's about rethinking how we interact with alien environments. Every mission to Mars will be a dance with dust, a silent negotiation between human ingenuity and a planet that doesn't welcome visitors. The suits that succeed won't just protect astronauts from the obvious dangers like radiation or vacuum. They'll have to outsmart an adversary that's always present, always drifting, and always waiting for a chance to breach the fragile line between survival and disaster. Because on Mars, the greatest threat might not be the vast, empty void above, but the tiny, relentless particles underfoot. Radiation is the silent killer of space travel, an invisible threat that doesn't announce itself with dramatic cracks or alarms. Unlike the immediate dangers of vacuum or extreme temperatures, cosmic rays and solar particles work slowly, penetrating spacesuits and human tissue alike, damaging cells in ways that can lead to cancer years later. Earth's magnetic field shields us from the worst of it, but beyond that protective bubble, astronauts are exposed to radiation levels hundreds of times higher than anything on the ground. A single solar storm could deliver a lethal dose in hours, while the constant barrage of galactic cosmic rays, tiny, high-speed atomic nuclei from distant supernova would erode health over time. On Mars, where the atmosphere is too thin to offer meaningful protection, this isn't just a risk, it's a deal-breaker. Traditional shielding relies on mass, thick layers of lead or aluminum to absorb radiation before it reaches the body. But hauling that kind of weight to Mars is impossible. Every extra kilogram means more fuel, more cost, and less room for critical supplies. That's why researchers are turning to smarter solutions like hydrogen-rich materials. Hydrogen's tiny atomic structure makes it incredibly effective at scattering radiation without adding bulk. Imagine a suit lined with polyethylene, a plastic packed with hydrogen atoms, or even pockets of water woven into the fabric. Water isn't just for drinking, it's a surprisingly efficient radiation shield. And some designs propose wearable water walls, flexible bladders that astronauts could fill from local ice deposits on Mars or the Moon. But what if we could deflect radiation instead of just absorbing it? Enter magnetic shielding, a concept borrowed from futuristic spacecraft. Miniature electromagnetic coils embedded in the suit could create a personal magnetic field, gently bending charged particles away from the wearer. It's like holding an umbrella in a downpour, except this umbrella bends the rain around you. Early prototypes are still power-hungry and bulky, but advances in superconducting materials could make this sci-fi idea a reality. The real game-changer, though, might be metamaterials, engineered substances with properties not found in nature. Some of these exotic materials can manipulate electromagnetic waves, potentially redirecting radiation like a mirror reflecting light. Others use intricate nanostructures to absorb and dissipate harmful energy. One lab is testing a metamaterial that rearranges its atoms in response to radiation, effectively healing its shielding properties over time. None of these solutions are perfect alone, which is why the best designs will likely combine them, layering hydrogen-rich fabrics with magnetic deflectors and metamaterial patches, creating a multi-layered defense. Because when it comes to radiation, redundancy isn't optional. A single gap in protection could mean irreversible damage. the challenge isn't just technical, it's biological. We still don't fully understand how long-term exposure to deep space radiation affects the human body. Until we do, the safest approach is to assume every particle is a potential threat. That's the paradox of radiation shielding. The more we learn, the more we realize how much we still need to invent. But one thing's certain, the suits that take humans to Mars won't just be armor. They'll be the most advanced radiation labs ever worn, constantly adapting to an invisible enemy we're only beginning to understand. Powering a spacesuit for months or even years on an alien world isn't like charging a smartphone. It's a life or death equation with zero room for error. Solar panels, the go-to solution for satellites and rovers, hit their limits when faced with Mars' months-long dust storms or the permanent shadows of lunar craters. A suit that goes dark in those conditions isn't just inconvenient, it's a coffin. That's why engineers are turning to radical alternatives, from nuclear batteries that last decades to wireless power beamed through the void. Take radioisotope thermoelectric generators, or RTGS, a mouthful of a name for what's essentially a nuclear battery. These devices convert heat from decaying radioactive materials like plutonium-238 directly into electricity. No moving parts, no sunlight required, just steady power for years on end. RTGS have kept missions like Voyager and Curiosity running long past their expected lifespans, surviving environments that would kill conventional systems. For a spacesuit, a scaled-down version could be sewn into the backpack life support unit, providing uninterrupted energy whether the wearer's trekking through a dust-choked Martian valley or exploring the frozen wastes of Europa. The catch: radioactive materials are heavy, tightly regulated, and raise concerns about safety if a suit were damaged. But with advances in shielding and miniaturization, next-gen RTGS could be both lightweight and fail-safe, encased in materials that absorb radiation before it ever reaches the astronaut. Then there's the wild card: wireless energy transfer. Imagine a lunar base equipped with microwave or laser transmitters, silently beaming power to suits miles away. Astronauts could venture into permanently shadowed craters, where sunlight never reaches without worrying about their batteries dying. Early experiments have shown it's possible, with teams successfully transmitting energy over distances of several kilometers here on Earth. The technology borrows from principles used in wireless charging pads, just scaled up dramatically. For Mars, where dust storms can last months, orbiting solar satellites could collect sunlight above the haze and beam it down to the surface, creating a global power grid that never goes offline. But wireless isn't perfect. Beaming energy through the atmosphere, or lack thereof, requires precise alignment. A misaligned receiver could mean lost power or even accidental overheating. And while the technology avoids the weight of batteries, it introduces new complexities like suit-mounted receivers that don't hinder movement. Some prototypes use lightweight, flexible antenna arrays woven into the outer fabric, while others explore resonant coupling, a method that transfers energy efficiently over short distances without dangerous beams. The real breakthrough might lie in hybrid systems. A suit could rely on compact RTGS for baseline power, wireless charging for high-demand tasks, and ultra-efficient lithium-sulfur batteries as a backup. Add in energy-harvesting fabrics that convert motion or body heat into trickle charges, and suddenly, power scarcity becomes a solvable puzzle. This isn't just about keeping the lights on. It's about enabling explorers to push farther, dig deeper, and stay longer than ever before. Because the difference between a fleeting visit and a lasting presence on another world might come down to something as simple as a battery, or as revolutionary as a pocket-sized nuclear reactor. A spacesuit is more than a life support system, it's a second home. When astronauts spend months or even years inside these suits during surface missions, every pinched joint, every awkwardly placed control panel, and every hour of discomfort isn't just an annoyance. It's a slow drain on morale, focus, and ultimately survival. Think about wearing a winter coat that's too tight for 6 straight months. Now imagine that coat could kill you if you scratch an itch wrong. That's the reality future Mars explorers face unless we rethink suits from the inside out, prioritizing human factors as much as radiation shielding or oxygen flow. Take mobility. Current suits force astronauts into a permanent slight hunch, arms bent like a boxer's, fighting against pressurized layers with every movement. On a 2-hour spacewalk, that's manageable. Over a 2-year mission, it's a recipe for chronic pain, muscle atrophy, and even spinal compression. Next-gen designs are tackling this with biomechanically optimized joints that align with natural motion, shoulder rings that rotate like human ball and socket joints, knee hinges that mimic tendon elasticity, and back supports that adjust posture dynamically. Some prototypes use soft robotics, air-filled bladders that inflate or deflate to share the workload with the wearer's muscles, reducing fatigue during long excursions. It's the difference between lugging a backpack uphill and having that backpack gently push you forward. But physical comfort is only half the battle. Isolation in an alien environment, where every sunrise is filtered through a visor and human touch is impossible, poses a psychological toll we're only beginning to understand. That's where virtual reality comes in. New helmet displays could project not just data, but calming Earth vistas, a forest canopy overhead during a Martian sunset, or a virtual window to mission controls smiling faces. Haptic feedback systems might simulate a reassuring hand on the shoulder from a teammate millions of miles away, using precise vibrations to convey presence. Even something as simple as adjustable lighting inside the helmet, shifting from cool blues to warm oranges, could help regulate circadian rhythms when planetary day-night cycles feel alien. Then there's the voice no one talks about, sound. Inside a traditional suit, your own breath is deafening, the whir of fans becomes a relentless hum, and radio static cuts in and out. It's sensory deprivation and overload at once. Acoustic engineers are now designing soundscapes for suits, noise-canceling algorithms that mute mechanical clatter while preserving voice clarity, even subtle background tones like distant bird calls or flowing water to combat the eerie silence of dead worlds. One NASA study found that astronauts who could curate their auditory environment reported significantly lower stress levels during simulations, the ultimate goal. A suit that doesn't just keep astronauts alive but makes them feel human. That means intuitive controls placed exactly where fingertips expect them, not buried under layers of clumsy gloves. It means materials that breathe and stretch like athletic wear, not stiff canvas. It means interfaces that adapt to individual preferences. Maybe one explorer needs constant mission updates in their display, while another prefers minimalist data to stay focused. These aren't luxuries. On a mission where every decision carries life or death stakes, comfort is performance. Mental fatigue can be as dangerous as a cracked visor. The lesson here transcends engineering. The suits that succeed won't just be technological marvels. They'll be psychological lifelines, carefully crafted to sustain the mind as fiercely as they defend the body. Because surviving another world isn't just about enduring, it's about thriving. Imagine needing the same suit to explore the scorching vents of an active Martian volcano and the frozen methane lakes of Titan. It's like asking a deep-sea diver to wear their wetsuit on a mountain climb. It just doesn't work. That's the fatal flaw of one-size-fits-all spacesuits. But what if astronauts could customize their gear like swapping tools on a multi-tool? Enter modular design, where suits transform from heavy-duty excavation armor to lightweight scientific gear with just a few clicks. The key lies in standardized connection points. Think USB ports, but for spaceware. A base layer handles life support and communications, while outer components snap on like Lego bricks. Need to collect samples on Mars? Attach reinforced gloves with built-in scoops and microscopes. Heading into a lunar lava tube, swap in extra thermal layers and a helmet-mounted LiDAR to map pitch-black tunnels. Even the boots are interchangeable, spiked for icy terrain, flexible for low-gravity leaps, or weighted for windy Martian dust storms. This isn't just about convenience, it's about survival. Europa's surface, for example, bombards explorers with radiation, while its subsurface ocean demands waterproof flexibility. A modular suit could transition between both extremes in minutes, no wardrobe change required. NASA's Z2 prototype already tests this philosophy with mix-and-match hard torso segments and soft limbs. But the real innovation comes from private firms like Final Frontier Design, whose suits use rotary seals that let astronauts twist components into place without tools. Picture a backpack that clicks into ports on the suit's spine, whether it's carrying extra oxygen, scientific instruments, or even a jetpack for emergency maneuvers. Some concepts go further with smart modules that self-diagnose wear and tear. A glove might flash a warning when its abrasion layer hits 50%, prompting a swap before it fails. The game changer, mission-specific AI. A modular suit headed for Titan's methane lakes could preload a library of movement algorithms optimized for liquid hydrocarbon swimming, while a moon miner's suit might prioritize joint reinforcement for wielding rock drills. These aren't passive costumes, they're adaptive machines that evolve with their environment. Yet the biggest win might be logistical. Instead of hauling 10 specialized suits to Mars, crews could bring 3 modular ones with 30 components, saving precious cargo space. Damaged parts get replaced, not discarded. A torn knee pad on Europa doesn't doom the entire suit. And when new threats emerge, like an unexpected radiation spike, Mission Control could remotely approve adding shield panels mid-mission. This flexibility rewrites the rules of exploration. Suddenly, a single astronaut can transition from geologist to engineer to emergency responder without missing a beat. The suit becomes less of a barrier and more of a partner, morphing to meet challenges we haven't even imagined yet. Because in the end, the best spacesuit isn't the one that survives alien worlds, it's the one that adapts to conquer them. Imagine a tiny crack forms in your spacesuit's glove during a critical Mars expedition. Back on Earth, you'd just grab a spare, but when the nearest hardware store is 34 million miles away, waiting for a resupply mission isn't an option. That's where 3D printing swoops in, not as a futuristic novelty, but as a lifeline. The next generation of spacesuits won't just withstand alien environments, they'll repair themselves using printers that turn discarded packaging, broken tools, or even Martian soil into emergency patches. This isn't sci-fi, it's the cutting edge of survival engineering. Traditional missions haul backups for every critical component, but that approach falls apart on multi-year journeys. A single suit might need hundreds of spare parts, seals, valves, joint bearings, each adding weight and eating into precious cargo space. 3D printing flips the script. Instead of carrying duplicates, astronauts bring raw materials and blueprints. A printer the size of a microwave could fabricate a cracked helmet latch from recycled plastic, or forge a new oxygen regulator nozzle using metal powder harvested from spent equipment. NASA already tested this aboard the International Space Station, where printers have manufactured wrenches, surgical tools, and even satellite components in zero gravity. The same tech scaled for planetary surfaces could mean the difference between a minor suit tear and a mission-ending catastrophe, but the real magic lies in the materials. Researchers are developing printers that work with regolith, the dusty, mineral-rich soil covering the Moon and Mars. Mix that regolith with a binding agent, and suddenly, your 3D printer can churn out ceramic joint reinforcements or radiation-shielding tiles on demand. One European Space Agency project even demonstrated printing entire habitat walls from simulated lunar dust. For spacesuits, this means armor patches could be sourced locally, reducing reliance on Earth shipments. The process isn't just about replacing broken parts. Smart suits of the future might embed 3D printers directly into their design. Picture a wrist-mounted microprinter that extrudes a temporary sealant over a micrometeorite puncture, buying time to reach safety. Or helmet visors that self-repair by depositing transparent polymers over scratches, maintaining clarity without manual intervention. These systems would work alongside AI diagnostics, identifying flaws and printing solutions before astronauts even notice the issue. Challenges remain, of course. Printing in low gravity can warp materials, and not every component can be replicated with recycled scraps. High-stress parts like knee joints or life support connectors might still require Earth-made spares. But the goal isn't total independence, it's resilience. A crew equipped with 3D printing isn't helpless when a dust storm cracks their suit's elbow joint or a rover mishap snaps a hose connector. They're resourceful, turning waste into solutions with the hum of a printer in the background. This shift changes more than just logistics. It rewrites the psychology of deep space exploration. Knowing you can fabricate a fix from almost nothing transforms fear into confidence. A torn glove becomes a solvable puzzle, not a death sentence. And that mindset, the belief that every problem has a workaround, might be the most vital tool we pack for the journey. Because when you're printing your own lifelines, the universe feels a little less hostile, and the future a little more within reach. Before a single spacesuit ever touches Martian soil, it faces trials far closer to home, places so harsh they might as well be alien worlds. Antarctica's vast ice sheets, where temperatures plunge to -60°C and winds howl at hurricane force, become stand-ins for Europa's frozen crust. Researchers clad in prototype suits trudge through blizzards, testing whether joints stiffen in deep cold or seals hold against relentless frost. A single loose thread here could mean a fatal leak on another planet. But it's not just about the cold. The desert valleys of Chile's Atacama, one of Earth's driest places, mimic Mars' parched landscape with eerie precision. Dust storms are simulated using industrial fans and crushed volcanic rock, probing whether suit filters clog or electronics overheat when coated in fine grit. Then there's the underwater lab off the coast of Florida, where astronauts train in NAS, a neutral buoyancy laboratory, a massive pool mimicking the weightlessness of space. Here, engineers observe how suit mobility holds up during hours of simulated repairs on a mock lunar lander. Every awkward reach, every strained twist reveals design flaws invisible on dry land. But the most telling tests happen in Hawaii's lava tubes, pitch-black caverns where GPS fails and communication drops to echoes. Teams navigate these labyrinths with only helmet lamps to guide them, rehearsing for the isolation of Martian caves or the icy tunnels of Enceladus. These aren't just drills, they're controlled disasters. Engineers intentionally stress suits beyond breaking points, because uncovering a weak hinge or a faulty oxygen sensor in Antarctica means fixing it before someone's life depends on it. At Arizona's Biosphere 2, Sealed environments let scientists study how suits interact with habitats over weeks, tracking whether toxic dust hitchhikes indoors or suit materials off gas harmful chemicals in confined spaces. Even sweat becomes data. In Utah's Mars Desert Research Station, volunteers log how often they need to adjust temperature settings during simulated rover deployments, revealing real-world comfort gaps no lab could predict. The philosophy is simple: fail here and you won't fail there. When a glove tears during a volcanic ash test in Iceland, that's a victory, one less unknown waiting millions of miles from home. These earthbound extremes are more than proving grounds. They're the final exam every spacesuit must pass before earning its ticket to the stars, because in the end, the best designs aren't born in spotless labs. They're forged in dust, ice, and darkness, where every flaw uncovered is a life saved. The race to build the next generation of spacesuits isn't just a scientific challenge. It's a high-stakes collaboration between governments and private companies, each bringing unique strengths to the table. NASA, with decades of hard-earned experience from Mercury to the International Space Station, understands the life-or-death precision required for space exploration. But when it comes to rapid innovation, agencies like NASA are increasingly turning to partners like SpaceX, Boeing, and a wave of ambitious startups, blending institutional knowledge with Silicon Valley-style agility. The result, a revolution in suit design that's moving faster than ever before. Take SpaceX's sleek, minimalist suits, for example. Designed primarily for crewed flights aboard the Dragon capsule, these pressure garments prioritize mobility and comfort over planetary exploration, a stark contrast to NASA's traditional bulk. Where old-school suits were essentially mini spaceships with layers of redundancy, SpaceX's approach strips away non-essentials, relying on the capsule's environment for backup. It's a philosophy rooted in the company's broader ethos, lighter, faster, and hyper-focused on the mission at hand. But this private sector speed comes with trade-offs. While SpaceX can iterate quickly, testing new materials or ergonomic tweaks in months rather than years, their suits aren't yet built to handle the brutal dust storms of Mars or the icy vacuum of deep space. Boeing, on the other hand, bridges the gap between government caution and corporate innovation. Their blue and white Starliner suits, while still designed for launch and re-entry, incorporate advanced composites and 3D printed components that reduce weight without sacrificing safety. Boeing's deep aerospace heritage gives them an edge in rigorous testing protocols, but they've also adopted rapid prototyping techniques more common in tech startups. One game-changing feature, touchscreen-compatible gloves, a nod to the increasingly digital cockpits of modern spacecraft. It's a small detail with huge implications, proof that private companies are rethinking even the most basic assumptions about how astronauts interact with their gear. Meanwhile, startups like Final Frontier Design and Collins Aerospace are pushing boundaries with radical ideas that might never emerge from traditional government workshops. Final Frontier, founded by former NASA engineers, focuses on mechanical counterpressure suits, skin-tight designs that could replace bulky gas-pressured layers. Their approach treats spacesuits like extreme athletic wear, borrowing from advancements in sports medicine and high-performance textiles. Collins, meanwhile, experiments with modular, plug-and-play components, allowing suits to be customized for everything from lunar walks to emergency repairs. These smaller firms thrive on risk, testing concepts that larger entities might dismiss as too experimental. NASA a role in all this, less gatekeeper, more matchmaker. Through programs like the Commercial Crew Program and Next Step, the agency funds private development while providing access to decades of hard-won data. They've learned that sometimes the best way to innovate isn't to build everything in-house, it's to create a competitive ecosystem where the brightest minds, whether in government or private labs, can sprint toward the same goal. The agency's own next-gen suit, the X-EMU, embodies this hybrid philosophy. It incorporates lessons from Apollo-era durability while embracing private sector advances in mobility and materials. The beauty of this partnership model lies in its diversity of thought. Government programs offer unmatched rigor and long-term vision. Private companies bring speed, specialization, and a tolerance for failure that fuels breakthroughs. And startups, they're the wild cards challenging conventions with every stitch and circuit. Together, they're proving that the future of spacesuits isn't just about better technology, it's about better collaboration. Because when the goal is surviving alien worlds, no single organization has all the answers, but together they might just have enough to get us there. Building a spacesuit that can withstand alien worlds isn't just an engineering challenge, it's a financial tightrope walk. The latest prototypes, packed with self-healing fabrics, AI diagnostics, and radiation-deflecting metamaterials, come with price tags that could fund a small city. NASA's next-gen X-EMU suit, for example, carries an estimated cost of over $150 million per unit. That's more than some spacecraft. But here's the brutal reality. As we shift from government-led missions to commercial spaceflight, every gram and every dollar matters. The question isn't just, can we build it? It's, can we afford to? This dilemma has sparked a fierce debate in aerospace circles. On one side, traditionalists argue that cutting corners on suits is a death sentence. You can't put a price on survivability when a single flaw means catastrophe. They point to the Apollo program, where no expense spared engineering saved lives, like when a torn glove on the moon nearly exposed an astronaut's skin to vacuum. But the other side counters with a radical idea. What if some suits weren't built to last? For short-term lunar base construction or rapid Mars surveys, disposable suits, think high-tech hazmat gear, could slash costs while still providing baseline protection. Private companies like Axiom Space are already experimenting with this approach, using modular designs where only the contaminated or damaged components get replaced, not the entire suit. The economics get even trickier when you factor in who's footing the bill. Government agencies like NASA or ESA operate with taxpayer money, where safety margins are non-negotiable. But for a SpaceX or Blue Origin mission where profitability looms large, the calculus changes. A tourist paying $50 million for a joyride to the moon's orbit might not need or want a suit capable of surviving Martian dust storms. This divide is giving rise to a two-tiered market: bespoke, ultra-resilient suits for explorers and lean, task-specific models for commercial crews. Materials science plays a huge role in this cost equation. Graphene might block radiation better than lead, but it's astronomically expensive to produce in suit-sized quantities. That's why researchers are exploring compromises, like sandwiching cheaper materials between thin graphene layers. Similarly, 3D printing could reduce waste by fabricating custom-fit components on demand, rather than machining one-size-fits-all parts from costly titanium blocks. Even the humble zipper gets scrutinized, replacing airtight metal ones with lightweight, laser-welded polymer seams might save kilograms and millions over a fleet of suits. But the real wild card is reusability. Traditional suits degrade with every use, their layers battered by micrometeorites and abrasive dust. What if future designs could be refurbished instead of replaced? Imagine a suit returning from Mars, its outer shell scoured by sandstorms, getting dipped in a nanomaterial bath that fills microscopic cracks and restores radiation shielding. Startups like SpaceForge are pioneering such self-renewing materials, though the tech is still in its infancy. The bottom line, there's no perfect answer. A Mars colony will need both premium suits for hazardous excursions and budget-friendly options for routine tasks. The winning designs won't just push technological boundaries, they'll balance them against the cold, hard math of interstellar economics. Because in the end, the suits that take us to the stars won't just be triumphs of science, they'll be masterpieces of compromise. Who gets the cutting-edge suit when there aren't enough to go around? This isn't just a logistics problem, it's a moral minefield. Picture a Mars mission where only half the crew has radiation shielding upgrades, or a lunar base where scientists studying water deposits compete with security personnel for the only suit rated for extreme cold. These aren't hypotheticals. As we push deeper into space, the scarcity of advanced life support technology forces brutal choices that reveal our priorities as explorers. Historically, militaries have driven spacesuit innovation. Think of the Air Force pilots who tested early pressure suits in the 1950s. Their needs shaped designs for decades, prioritizing durability and emergency response. Scientists, meanwhile, often adapted existing suits for research, sacrificing mobility for payload space. But today's missions blur these roles. A biologist collecting Martian soil samples needs agility and dexterity, while a security officer patrolling a lunar outpost requires armor-like protection against micrometeorites. So who deserves the limited supply of next-gen suits? One argument favors scientists. Their work unlocks the discoveries that justify the mission's cost. A geologist in a high-mobility suit could scale cliffs to access pristine rock layers, revealing Mars' geological history. A botanist testing greenhouse prototypes might need lightweight, breathable materials to work for hours in habitat modules. Prioritizing research could maximize the mission's scientific return, turning every suit into a tool for expanding human knowledge. But others counter that safety must come first. Military or security personnel often face the highest risks venturing into uncharted terrain to scout landing zones or rescue stranded teammates. Giving them the most advanced suits isn't about privilege, it's about ensuring the entire crew's survival. A single equipment failure during a sandstorm could strand an unprepared team, turning a routine outing into a catastrophe. In these scenarios, the toughest suits act as insurance policies for everyone. Then there's the wild card, commercial interests. As private companies join the space race, suits could become perks for the highest bidders. Imagine a billionaire tourist leasing a graphene-lined suit for a moonwalk, while the base's engineers make do with older models. While this sounds dystopian, it's already happening. Civilian orbital flights offer custom-fit gear for passengers, while NASA astronauts share standardized suits. The danger, a two-tiered system where safety becomes a luxury. The heart of the debate isn't just about suits, it's about values. Do we prioritize the collective good, individual survival, or the democratization of space? There's no easy answer, but one thing's certain. As we design suits for alien worlds, we're also designing the ethical framework for how we'll inhabit them. Because in the end, the technology that protects our bodies will also define our humanity. The moment an astronaut steps onto another world, their suit isn't just life support, it's a symbol. Think about the Apollo era, a 7LB suit. Its gleaming white torso and gold visor reflecting the sun against the lunar dust. That image didn't just define a mission, it shaped humanity's collective imagination. For millions watching on grainy television screens, that suit became the physical embodiment of exploration, a wearable flag planted in the cosmos. And that's the untapped power of spacesuit design. When form meets function in just the right way, it doesn't just protect astronauts, it inspires generations. Consider how differently we'd view space travel if those first moonwalkers had worn bulky, industrial-looking gear devoid of elegance. Would the public have been as captivated? Unlikely. The A7LB's streamlined silhouette, with its exaggerated ribbing and helmet's reflective glare, wasn't just practical, it was cinematic. It turned astronauts into archetypes, their suits as recognizable as superhero costumes. That visual shorthand still lingers. When filmmakers or advertisers want to evoke the future, they often riff on those same design cues. The lesson: aesthetics matter. A well-designed suit doesn't just serve its wearer. It tells a story, one that can rally support for ambitious missions or make the abstract idea of interplanetary life feel thrillingly tangible. This symbology extends beyond nostalgia. Private companies now leverage suit design as branding. SpaceX's sleek, all-white pressure garments, with their minimalist helmets and tailored fit, scream 21st century explorer in a way that resonates with younger audiences. Compare that to NASA's upcoming X-Emu with its bold red stripes and modular components, a deliberate nod to inclusivity, signaling that space belongs to everyone. These choices aren't accidental. They're calculated to shape public perception, to make Mars missions feel less like government projects and more like humanity's next grand adventure. But the cultural impact runs deeper than marketing. Spacesuits are rare examples of technology that bridge the gap between utilitarian tool and cultural artifact. A medieval knight's armor spoke of their status and role. Similarly, a suit's design telegraphs the values of its era. The clunky, rivet-covered suits of 1950 sci-fi reflected Cold War anxieties about mechanization. Today's prototypes, with their biomimetic fabrics and AI interfaces, mirror our obsession with seamless tech integration. Even the shift toward customizable, modular suits hints at a broader cultural trend: the rejection of one-size-fits-all solutions in favor of personal expression. The stakes here are higher than they seem. Public enthusiasm fuels funding, and funding determines how quickly we reach Mars or Europa. A suit that captures the imagination, whether through nostalgic callbacks or futuristic minimalism, can turn skeptics into supporters. Imagine a child seeing an astronaut's suit on Titan, its design echoing their favorite video game or sci-fi film. That connection might ignite a passion that lasts a lifetime, potentially recruiting the next generation of engineers or explorers. So while engineers obsess over radiation shielding and joint mobility, designers wield their own kind of power. They're crafting the visual language of humanity's future, one stitch, one visor, one iconic silhouette at a time. Because the right suit doesn't just protect the body, it ignites the collective spirit, transforming distant planets into places we can see ourselves calling home. Early spacesuits weren't just built for space, they were built for men. The iconic designs of the Apollo era followed a one-size-fits-all approach tailored to the average male astronaut's proportions. For women like Sally Ride, the first American woman in space, that meant stuffing into suits designed for broader shoulders, longer torsos, and larger hands. Gloves gaped at the fingertips, forcing astronauts to curl their fingers to grip tools. Boots slipped during moonwalks, risking twisted ankles in low gravity. Even the life support backpacks, optimized for male center of gravity, sat awkwardly on female frames, throwing off balance during critical tasks. These weren't just minor inconveniences, they were safety hazards disguised as tradition. But change is coming from an unexpected source. A new generation of female engineers rewriting the rules of suit design. Take NASA's Amy Ross, a spacesuit engineer who spent her career advocating for adjustable components. Her work on the X-Emu suit introduces interchangeable parts, modular torsos, scalable limb segments, and gloves with adjustable palm widths. Suddenly, a single suit can accommodate a 5'2" scientist and a 6'4" pilot without compromise. The secret lies in 3D scanning astronauts to create custom-fit pressure layers, then using sliding joint rings and telescoping struts to fine-tune mobility. It's a radical shift from the old paradigm of forcing bodies into rigid templates. The push for inclusivity goes beyond sizing. Traditional suits often treated female physiology as an afterthought, leading to overlooked risks. For example, radiation shielding optimized for male torso thickness left critical organs vulnerable in smaller frames. New designs account for these differences, integrating variable shielding densities and repositioned life support hoses to avoid restricting mobility during repetitive tasks like sample collection. Even something as simple as bathroom access, a notorious challenge in old suits requiring hours of fluid restriction, gets reimagined with gender-sensitive waste management systems. Private companies are leapfrogging ahead too. Startups like Final Frontier Design collaborate with female astronauts to test suits in parabolic flights, gathering real-time feedback on pinch points long ignored by male-dominated design teams. Their gloves, for instance, now feature tapered fingertips and flex zones at the knuckles, addressing decades of complaints about hand fatigue. Meanwhile, MIT's Space Exploration Initiative explores biomorphic designs inspired by nature, suits that move like a second skin, adapting to individual anatomy rather than resisting it. The impact of this shift transcends engineering. Every time a woman steps into a suit crafted for her body, it sends a message: space belongs to everyone. Young girls watching footage of astronauts like Jessica Meir or Christina Koch don't see ill-fitting gear forcing adaptation. They see tools designed to empower. And that visibility matters. When spacesuits finally reflect the diversity of those who wear them, it's not just about closing the gender gap in design. It's about opening the cosmos to a future where no one has to squeeze into someone else's idea of an explorer. Astronauts don't just train to use their suits, they train to lose them. Or at least that's the terrifying premise behind some of the most intense simulations on Earth. Picture this: you're submerged in a massive pool, weighted to mimic Mars' gravity, when suddenly your glove tears. Water rushes in, simulating a catastrophic pressure leak. Your heart rate spikes, but your training kicks in. You clamp one hand over the breach while scrambling for an emergency sealant patch. This isn't a scene from a disaster movie. It's a routine drill at NASA, a neutral buoyancy lab, where every second of hesitation could mean the difference between life and death on another world. These simulations go far beyond textbook scenarios. In Arizona's lava tubes, astronauts navigate pitch-black caverns with only helmet lamps, rehearsing how to repair a suit's torn knee pad when no help is coming. At the European Space Agency's underground caves in Sardinia, teams practice for days in total isolation, troubleshooting mock oxygen failures or communication blackouts. The goal isn't just to survive, it's to adapt, because on Mars or Europa, there's no mission control to walk you through an emergency. The suit isn't just your lifeline, it's your only teammate. One of the most brutal tests happens in Canada's Arctic, where temperatures plunge to -40 degrees Celsius. Astronauts wear prototype suits with deliberate flaws. A stuck zipper here, a malfunctioning heater there, forcing them to improvise fixes with whatever tools they've got. The lesson: panic is a luxury you can't afford. When your visor fogs up during a Martian dust storm, or your cooling system fails mid-climb, the solution might lie in repurposing a backup battery or rerouting a hose. These aren't skills you learn in a classroom. They're forged in environments so hostile They strip away every assumption about safety, but the real genius of these programs lies in their psychological toll. Trainees spend weeks in simulated missions where suit failures strike at random, sometimes during sleep, sometimes mid-task. The stress is relentless by design. Because when you're millions of miles from home, exhaustion and fear will be your constant companions. Learning to function through that fatigue, to make split-second decisions when your pulse is racing and your hands are numb, is what turns an astronaut into a survivor. The takeaway: the best spacesuit isn't just the one with the toughest fabric or smartest tech. It's the one its wearer knows inside and out, every seam, every backup, every last-ditch workaround. Because in the end, no matter how advanced the suit, the human inside it remains the most unpredictable variable of all. And that's exactly why we train for the unknown. Not to conquer fear, but to carry it with us and still get the job done. Right now, if a private space company builds a spacesuit, there's no universal rulebook telling them how safe it has to be. Unlike aviation, where every bolt and wire is governed by decades of international treaties, the world of commercial spaceflight is a legal Wild West. A startup could, in theory, send tourists to orbit in suits held together with duct tape and prayers, as long as they're not breaking any national laws, which themselves are patchy at best. This isn't just hypothetical. In 2020, during an uncrewed test flight of SpaceX's Starship, a prototype spacesuit was photographed with visible stitching and uneven seams far from the rigorous standards of NASA, a legacy design. No one stopped the flight because no one had the authority to say it wasn't safe enough. The risks here aren't just about shoddy craftsmanship. Without unified safety standards, companies face a dangerous incentive: cut corners to move faster. Imagine a scenario where two firms compete to launch the first paid Mars mission. One spends years perfecting a radiation-proof suit with triple redundancies. The other slaps together a cheaper model, betting that the slim odds of a catastrophic failure won't outweigh the PR win of being first. In the vacuum of space, that gamble could cost lives and set back public trust in space exploration for decades. Even more troubling, the legal gray zone extends to liability. If a passenger dies on a commercial lunar flight due to a faulty suit, who's responsible? Current space treaties, drafted in the 1960s, were written with governments, not corporations, in mind. The Outer Space Treaty vaguely states that nations must supervise their private companies, but it doesn't specify how. That leaves a maze of conflicting national regulations. The U.S. requires FAA approval for launches but has no equivalent for spacesuit safety. The UE, racing to become a space tourism hub, offers tax breaks to space firms but minimal oversight. And some countries, eager to attract investment, might look the other way entirely. The solution isn't as simple as copying aviation rules. Space is fundamentally different. A plane can glide to an emergency landing. A suit failure in orbit leaves no room for error. That's why experts propose a tiered system: basic safety floors for suborbital joyrides and stringent Apollo-level standards for deep space missions. Groups like the International Association for the Advancement of Space Safety are pushing for global guidelines, but progress is slow. Meanwhile, the private sector isn't waiting. Companies like Axiom Space are self-regulating, inviting third-party audits of their suit designs, while startups like Orbital Outfitters share testing data openly to build industry-wide trust. The stakes couldn't be higher. A single high-profile suit failure could trigger a regulatory crackdown so harsh it stifles innovation, or worse, public backlash that starves funding for exploration altogether. The golden age of spaceflight shouldn't be a race to the bottom. It should be a collaboration where competition drives progress, not recklessness. because in the end, the rules we write today won't just protect astronauts. They'll define how humanity steps safely into the cosmos. The Moon and Mars might both be barren, airless worlds, but their challenges for spacesuit designers couldn't be more different. Picture the Moon's surface, a landscape littered with regolith, jagged particles forged by meteor impacts over billions of years. These tiny shards act like microscopic glass shards, slicing through unprotected fabric with terrifying ease. Now contrast that with Mars, where dust isn't just sharp, it's mobile, whipped into planet-wide storms that can blot out the sun for months. One environment grinds you down with relentless abrasion, the other buries you in a suffocating haze. And that's just the start of the divide. Lunar suits face a silent, static threat. Without wind or weather, moon dust doesn't blow away. It clings electrostatically, coating every surface like a corrosive blanket. Apollo astronauts quickly learned how dangerous this could be. Their suits' layers wore thin after just a few excursions, and the abrasive grit jammed zippers, scratched visors, and even infiltrated their habitat, irritating lungs and fouling equipment. Future moonwalkers will need suits armored with ceramic coatings or self-cleaning surfaces that repel dust at the molecular level. Joints must be sealed tighter than a submarine's hatch, because on the moon, there's no atmosphere to slow a pressure breach. Every step kicks up particles that hang suspended in the vacuum, waiting to infiltrate. Mars, on the other hand, is a world in motion. Its dust storms aren't just inconvenient, they're planetary events with winds reaching hurricane speeds despite the thin air. But here's the twist, it's not the wind that's deadly. Martian storms are more like sandblasters operating in slow motion, with fine particles scouring everything in their path. Worse, this dust carries perchlorates, toxic chemicals that can burn skin and poison habitats if tracked inside. A Martian suit needs active defense systems, like electrostatic repulsion fields or airlock decontamination protocols, to prevent these particles from becoming a creeping hazard. And unlike the Moon's predictable 14-day nights, Mars serves up wild temperature swings. A suit's thermal systems must adapt to baking midday heat and bone-chilling nights without missing a beat. The gravity gap adds another layer of complexity. On the Moon, where gravity is 1/6 of Earth's, suits can afford some bulk. Astronauts bound across the surface in near weightless leaps, so minor mobility restrictions matter less. But Mars' 3/8 gravity is a tweener, too strong for effortless hopping, too weak for Earth-like movement. Here, suits must strike a delicate balance, armored enough to resist dust storms yet agile enough for tasks like climbing rock faces or repairing solar arrays. Every extra gram of protection makes movement more exhausting, and on a 2-year mission, fatigue can snowball into catastrophe. Then there's the question of duration. Moon missions might last weeks, Mars expeditions could stretch into years. A lunar suit can get by with simpler life support systems, knowing resupply is relatively close. But a Martian suit must be near autonomous, recycling every drop of sweat and breath with flawless precision. Its power systems can't rely on frequent battery swaps. They'll need nuclear options or solar panels that self-clean during dust storms. Even the gloves tell different stories. Moon gloves prioritize puncture resistance against sharp rocks, while Mars gloves might integrate toxin-scrubbing layers to handle perchlorate-laced soil. The takeaway: there's no universal spacesuit. The Moon demands a fortress against a silent, razor-filled wasteland. Mars requires a dynamic survival shell that outsmarts wind, poison, and isolation. Trying to build one suit for both would be like designing a single vehicle to race in the Sahara and the Arctic, possible in theory, but doomed in practice. And that's the beauty of this challenge. By embracing these worlds' extremes, we're not just solving technical puzzles. We're learning how to tailor technology to the universe's whims, one hostile environment at a time. While NASA and private companies dominate headlines, the race to reinvent the spacesuit is unfolding on every continent, with each player bringing unique philosophies to the challenge. Take Russia's Orlan suit lineage, a design as rugged as Siberia itself. Originally developed for the Soviet lunar program, these semi-rigid suits have evolved through 30 iterations, prioritizing brute force durability over flashy tech. Their latest variant, the Orlan ISS, trades NASA touchscreen gloves for analog dials and manual override switches, a deliberate choice. Cosmonauts train for worst-case scenarios where electronics fail, and their suits reflect that mindset. Thick aluminum alloy rings protect critical joints from micrometeorites, while nested layers of insulation handle temperature swings during spacewalks that often exceed 8 hours. It's a stark contrast to SpaceX's minimalist approach, proving there's more than one path to survival in the void. China's Fashion suit program reveals an entirely different strategy. Developed in parallel with their Tiangong space station, these suits blend cutting-edge materials with cultural symbolism. The striking blue and white color scheme isn't just aesthetic, it visually distinguishes Chinese astronauts during extravehicular activities, a subtle but powerful statement of national identity among the stars. But the real innovation lies in their modular life support backpack, which docks directly to the station's exterior. Unlike NASA suits that recycle air internally, the Fashion can plug into the station's supply like a scuba diver connecting to a surface air hose. This extends operational time dramatically, though at the cost of tethering astronauts close to their spacecraft. For China's methodical, infrastructure-first approach to space, it's a perfect fit. Europe's contribution might be the most surprising. Rather than building standalone suits, the European Space Agency has pioneered smart skins, wearable sensor layers that could upgrade any nation's gear. Their Eden project embeds microfluidic tubes directly into fabric, allowing suits to sweat away heat like human skin. Another breakthrough, the Biosuit from Portugal, which replaces gas pressurization with mechanical counterpressure using electroactive polymers. When electrified, these artificial muscles contract to hug the body with precise force, offering near-total mobility. The catch: it requires a skin-tight underlayer that's proven controversial among some astronauts. Yet this willingness to challenge century-old pressure suit dogma exemplifies Europe's strength. They're not just iterating, they're reimagining. The beauty of this global effort lies in its diversity of thought. While NASA chases Mars-ready durability and Russia prioritizes analog reliability, China builds seamless station integration and Europe explores biomechanical frontiers. This isn't redundancy, it's a distributed laboratory where every breakthrough benefits all. When a Portuguese polymer innovation gets tested on the International Space Station by a Russian cosmonaut wearing American boots, humanity inches closer to suits worthy of the cosmos. The future won't belong to any one nation's design. It'll be forged in the friction between them, where competition sparks the leaps that carry us further than any single vision could alone. Interstellar travel flips every rule of spacesuit design on its head. The suits that take humans to Proxima Centauri won't just endure years, they'll need to last centuries, surviving cosmic radiation, micrometeorite showers, and the slow decay of materials in deep space. Forget patching a gloved tear on Mars. These suits must self-repair across generations, with no resupply missions or repair crews. The answer might lie in hibernation-compatible designs, where suits double as cryogenic pods. Picture a second skin lined with microfluidic channels pumping hibernation drugs, slowing metabolism to near zero while nanobots patrol the fabric, mending atomic scale wear before it spreads. It's not just about surviving the journey, it's about waking up functional after 200 years of silent, frozen transit. The armor for such a voyage can't rely on today's materials. Galactic cosmic rays, high-energy particles from distant supernova would shred conventional shielding over decades. Instead, interstellar suits might weave layers of programmable matter, materials that rearrange their atomic structure in response to threats. Imagine a chest plate that thickens when radiation spikes, or a visor that darkens automatically near a flare star. Some theoretical designs incorporate quantum armor, exploiting entangled particles to dissipate energy across parallel dimensions, effectively spreading the impact of a micrometeorite across multiple realities. While this sounds like science fiction, labs are already experimenting with metamaterials that bend electromagnetic waves in ways once thought impossible. The suits of the 22nd century could make today's radiation shielding look as primitive as chainmail. Power systems face their own revolution. A suit traveling light years from any star can't rely on solar panels. Miniaturized fusion reactors, fueled by isotopes harvested from interstellar hydrogen, might provide steady energy for centuries. Or consider bioluminescent bacteria engineered into suit linings, feeding on waste CO2 to generate light and heat, a self-sustaining ecosystem wrapped around the wearer. The ultimate backup, kinetic energy harvesters that convert every footstep into stored power, ensuring motion itself becomes a lifeline. But the most radical shift isn't technical, it's philosophical. These suits won't just protect individuals, they'll safeguard entire lineages. A generational ship's crew might pass their suits down like heirlooms, each patch and repair telling a story. The stitching could encode vital data to how to fix a leak when the original engineers are centuries dead, or where to find replacement parts in alien star systems. The suit becomes a living archive, a blend of tool and teacher. The challenges are staggering, but so are the stakes. A single flaw in an interstellar suit doesn't mean a failed mission, it means extinction. That pressure is already driving breakthroughs today. Every experiment in self-healing polymers, every test of AI-driven predictive maintenance inches us closer to suits that might one day greet the light of another sun. When that day comes, the technology wrapped around those explorers won't just be their shield, it'll be their legacy. Redesigning spacesuits isn't just an engineering challenge, it's a declaration that humanity refuses to be bound by the limits of our atmosphere. Every stitch of self-healing fabric, every line of AI code predicting failures before they happen, is a step toward making alien worlds feel a little less alien. Think about what that means, the difference between watching Mars through a rover's camera and standing on its rust-colored surface, feeling the crunch of regolith under your boots because your suit handles the toxic dust like a second skin. That's the future we're building. The breakthroughs we've explored, modular armor that adapts to Europa's ice or graphene shielding that deflects cosmic rays, aren't just incremental upgrades. They're the foundation of a new era where survival gear becomes an extension of human ambition. Imagine a biologist on Enceladus, their suit's gloves heated just enough to melt ice samples without fogging the visor. Or a construction worker on the moon, their exoskeleton-assisted limbs lifting habitat panels with ease because the suit shares the load. These aren't fantasies. They're prototypes in labs today, waiting for their moment to leap from the drawing board to the stars. But here's the real magic. These suits won't just change how we explore space, they'll change who gets to explore. Custom-fit designs mean astronauts of all body types can venture farther and safer. Affordable materials could democratize access, turning spacefarers from an elite few into a diverse community of scientists, artists, and even tourists. The kid watching this video right now might wear one of these suits to hike Valles Marineris or dive into Europa's hidden ocean. That's the power of this technology. It's not just about surviving the cosmos. It's about making it feel like home. So what's next? The race is on. Private companies are iterating at breakneck speed, while agencies like NASA and ESA push the boundaries of materials science. Every breakthrough, whether it's a glove that repairs its own puncture or a visor that displays real-time radiation levels, gets us closer to suits that are less like tools and more like partners in discovery. The universe has always been the ultimate frontier, but for the first time in history, we're not just visitors passing through, we're getting ready to stay. If this vision excites you, you're already part of the story. Hit like if you want to see these suits in action, subscribe to follow the journey as it unfolds, and drop a comment with the alien world you'd explore first. The next chapter of space exploration isn't just being written, it's being worn, and with every innovation, we're stitching humanity's future into the fabric of the cosmos.